Chapter 1, Solid State by Aklesh sir. Topic covered in this chapter are 1. Unit cell, 2. Types of unit cell,
3. Bravais lattice. 4. Relationship between molar mass, density of the substance, and unit cell edge length. Welcome. Today we explore the unit cell. It is the smallest repeating unit in a crystal lattice, defining the structure of solids.
Formation of crystal structure. Meaning of lattice. Lattice is a geometrical arrangement of points. This position where atom can be placed, this is called space lattice. Here points are arranged in a three-dimensional periodic array. Here periodic array means that points are arranged in perfect order. Constituent particles such as atoms, ions, molecules form the basis of the crystal lattice that are attached to the lattice points. Here in animation you can see that atoms are positioned on the lattice point to form a crystal lattice. A crystal structure is obtained by attaching a constituent particle to each of the lattice points. Lattice is a point in a space, and basis is atom or ions. When bases are added to the lattice point, a crystal is formed.
Unit cell and crystal lattice.
We know that when many bricks combine together, they form a room. When many rooms combine together, they form a building. Similarly, when many lattice points combine together, they form a unit cell. When many unit cells combine together, they form a crystal lattice. So lattice point is like a brick, unit cell is like a room, and crystal lattice is like a big building which contains many unit cells. Now consider this 3D structure of a sodium chloride. This dot is one brick or one lattice point. This cube is one unit cell. This whole thing is a crystal lattice.
Unit cell and crystal lattice.
Looking at the definitions of unit cell and if I take a small structure that is a cubic structure, then I say that this simple small structure is nothing but unit cell, where I say that a unit cell is the smallest structural unit of crystal lattice. And this unit cell has a tendency of repeating itself in different directions. If you see on the screen, it is getting repeated in different directions. So I add to my statement by saying that a unit cell is the smallest structural unit of crystal lattice, which when repeated in different directions. So it repeats itself in different direction. So why it is repeating itself? It repeats to generate something called as the crystal lattice. And hence I say a unit cell is the smallest structural unit of crystal lattice, which when repeated in different direction generates the crystal lattice.
When the unit cells are stacked together to generate the crystal. Here below animation you can see the unit cells are stacked in all direction. Each unit cell shares its faces, edges and corners with neighboring unit cells.
Unit cell parameters. The dimensions of unit cell along the three axes. Consider simple cubic unit cell. There is three axes: X, Y and Z. The edge length along X-axis is denoted by symbol A. Y-axis it is denoted by symbol B. And along Z-axis it is denoted by symbol C. The angle between edge length B and C is represented by alpha. Angle between edge length A and C is represented by beta. And angle between edge length A and B is represented by gamma.
A unit cell is the smallest repeating unit in a crystal lattice. There are several types, which we will explore now.
Types of unit cell. There are 4 types of unit cells. 1. Primitive or simple unit cell. In primitive unit cell, the constituent particles are present at its corners only.
When constituent particles are present only on the corner positions of a unit cell, it is called as primitive unit cell.
In this model, orange spheres represent atoms and the sticks represent the edges of the unit cell. First, 4 atoms are connected to form a square base. Then atoms are added at the top and connected to form a cube. This cube represents a unit cell of a crystal lattice.
Today I will explain you the different type of unit cell. So first one, simple primitive unit cell. So here, see here, simple primitive unit cell. The constituent atoms are present only at the corner of a unit cell. So you can see here in my hand there is a simple primitive unit cell. In this ball indicates atom molecules. Okay, so in that atoms molecule I will say that the constituent particles or constituent atoms. So here the constituent atoms are present only at the corner position. So here you can see there are 8 atoms are present at the 8 corners of the unit cell. So 4 below, 1, 2, 3 and 4. Here above 1, 2, 3 and 4. There are total 8 atoms are present at the 8 corners of the unit cell.
In a crystal lattice, each unit cell are surrounded by neighboring unit cell. Here a corner atom is shared equally by 8 unit cells. 4 unit cells lie in the lower layer and 4 unit cells lie in the upper layer. Hence each corner of unit cell contribute 1/8 part of atom. Thus, 1 atom is present at each corner of the cube. Since each corner atom is shared by 8 unit cells, its contribution to 1 unit cell is 1/8. Therefore, the number of atoms in one simple cubic unit cell is 8 multiplied by 1/8, which is equal to 1.
How many number of atoms are present in the simple unit cell? So always remember that in a simple unit cell, each corner contribute 1/8. This is 1/8, this is 1/8, this is 1/8 of the total atoms. Okay, so it is not full atom, it is only 1/8 part of the atom is there. Okay, so this is 1/8, this is 1/8, 1/8, 1/8, 1/8, 1/8. So like that there is 8 atoms at the 8 corners. Okay, and each atom contribute 1/8. So total number of atoms contributed by the simple unit cell is equal to each corner contribute 1/8. So I will write here 1/8. How many corners are there? 1, 2, 3, 4, 5, 6, 7, 8. So multiply by 8 here. So cancel this. So here it will be 1 atom. So in a unit cell, only 1 atom are contributed by the simple unit cell.
Two, body-centered unit cell. In this type of unit cell, 1 constituent particle is present at the center of its body in addition to the corner particles.
Centered unit cell. In a centered unit cell, 1 particle, such as an atom, molecule, or ion, is located at the center of the unit cell. In addition to this central particle, particles are also present at each corner of the unit cell. This arrangement is why it is called a centered unit cell. Arrange 8 atoms in such a way that it will arrange at the corner of the cubic unit cell. and take on sphere and place it at the center of the unit cell. Here one atom as whole are present in inside the unit cell. In this we made a body-centered unit cell. And this is the result of body-centered unit cell. Eight atom at the corner end. And one atom in the center of body-centered unit cell.
Second topic, body-centered unit cell. Okay, so you'll see here, one constituent particles are present at the center of the body in addition to the corner particles. Okay, so it is present in the center also, it is present in the corner also. So we will see how to make body-centered unit cell. So to make that body-centered unit cell, this is 4 atoms I will place down. So what is the first one? The constant particles are present at the center of the body. So this is the this will going to present at the center of the center of the unit cell. So I will place the one atom at the center of the unit cell, and similarly one more I will take 4 atoms, okay, and I will place just above it. Okay, now you can see, and this type of structure is known as body-centered unit cell. Why it is called as body-centered unit cell? Because one atom is present at the center.
Body-centered unit cell. There are 8 atoms at each corner positions and 1 atom at its body center. As each atom at the corner position contributes 1/8 to the unit cell, the contribution of those 8 corner atoms to the unit cell is 1 atom. The atom at the center of the unit cell is not shared by any other unit
cell, making total of 2 atom per body-centered cubic unit cell.
We will now calculate the total number of atoms present in a body-centered unit cell. So total number of atoms present in body centered unit cell is equal to, see here, so each corner contribute 1/8, so I will write here 1/8. How many corners are there? 1 2 3 4 5 6 7 and 8. So plus into 8, 1/8 into 8, plus there is one atom at the center. Okay, as a whole one atom is there at the center. So one atom is at the center, and 1/8 into 8 atoms contributed by the corner, which is equal to 1/8 into 8 is 1, 1 plus 1 is equal to 2 atoms. So in a body centered unit cell, corner contribute 1 and the center contribute 1, total equal to 2 atoms.
Face unit cell consists of particles at the center of each of the faces, in addition to the corner particles. In this animation below, particles not only
are present not only at the corners but also at the center of each face of the unit cell.
In this model, the orange spheres represent atoms and the sticks represent the edges of the cube. Atoms are present at the 8 corners of the cube. Here I am connecting one sphere at the center of each face of cube to make a face-centered cubic crystal.
Third topic, face-centered unit cell. In this unit cell, particles of atoms are present at the center of the each face, in addition to the corner particles. So particles or atoms are present at the center of the each face. So here you can see this is a face-centered unit cell. In this you can see here that yellow part is the atoms which are present at the 8 corner of the unit cell, and this is how many faces are there. See, 1 face, 2 face, 3 face, 4 face, 5 face and 6 face. So total 6 phases are there, okay, and each phase is there is one atoms are present at the center of the each phase. One atoms are present at the center of the each phase. So here you can see there is one atom at one phase, one atom here, one atom here, one atom. Total 6 atoms are there at the center of the each phase.
Calculation of total No of atom present in face-centered unit cell. In below animation, face-centered unit cell has 8 atoms are at the corner and 1 atom are present in each face of cube. In face-centered unit cell, each corner atom contribute 1/8 of atom to one unit cell. So when all 8 corner 1/8 atom are joined, we get 1 atom. Total amount atom due to corner of unit cell is 1. Of each face of unit cell contain atom which contribute 1/2 of one unit cell. So when all 6 half atom of unit cell are joined, we get 3 atoms. So total atom is equal to 1 atom due to corner and 3 atom due to face centered. Total atom contributed by face centered unit cell equals 4.
How many atoms are contributed by this face unit cell? As we know that this corner atom contribute 1/8. Here I have written here, see, 1/8. So there are 8 corners. So 1/8 into 8. Okay, 1/8 into 8 is equal to 1 atom, which is contributed by the corners. Okay, so number of atoms contributed by the corner is equal to 1 atom. 1/8 into 8 is equal to 1 atoms contributed by the corners. And next, this is the part, this is a half part. Half part will be there in the unit cell. So each phase contribute half of the atom. So number of atoms contributed by the phase is equal to half into, this is a half part. How many half are there? 1, 2, 3, see here, again 1, 2, 3 and 4, 5 and 6. Okay, so 6 half atoms are there. So half into 6 face. So half into 6, 2 ones are 2, 2 3s are 6. Therefore there are 3 atoms. Okay, so total how many atoms are contributed by this face centered unit cell? 1 atoms contributed by the 1 atoms contributed by the corner and 3 atoms contributed by this face. So total there is 1 plus 3 is equal to 4 atoms. So face centered unit cell contribute 4 atoms in a unit cell. You can remember like that, F for face centered, F for 4.
Base-centered unit cell. This unit cell consists of particles at the center of any two of its opposite faces in addition to the corner particles.
In face-centered unit cell, particles are
present not only at the corners
but also at the center of any two of its opposite faces.
Fourth, end-centered or base-centered unit cell. Okay, see here. The constant particles are present at the center of any of the two opposite face in addition to the corner particles. So here you can see this is 4 atoms and there is one center atom. Okay, here also 4 atom, there is one center atom. So first what is written here, constant particles are present. Which constant particle here? This one, this yellow one. This constant particles are present at the center. You can see this atom is present at the center of these 4 atoms. Okay, the constant particles are present at the center of any of the two opposite face. So this is one face and this is one face. Okay, this is one face, this is one other face. Okay, so what I will do, I will place here like this. Of the two opposite faces, this is one face, one atom, this is another face, and this is opposite to each other. Okay, and addition to the corner particles, and there is 8 atoms are present at the 8 corners. 1, 2, 3, 4, 5, 6 and 7, 8. To calculate this, see, total number of atoms contributed by base centered unit cell. So, first thing, each corner atom contribute how many? 1 by 8. So there are how many 1 by 8? 1, 2, 3, 4, 5, 6, 7, 8. So total number of atoms present due to corner is equal to what? 1 by 8 into 8, which is equal to 1 atom. Okay. Here the unit cell has half of the atom. Always remember, at the face, if there is one atom is at the center, it will contribute a half. So this is the half part. Okay. So at this face there is a half atom. This is half atom, and below there is one half atom. Okay. So atom contributed by the opposite face of the unit cell is equal to, since at each face half atom is contributed, so here it is half into how many like this opposite face 2 atoms are there, here one half, here one half, so there is 2 position, so half into 2 position. Okay, just like here we have written 1 by 8 and 8 corners. Here also half, each is contributing half, like that there is 2 atoms. So half into 2 equal to 1 atom. So total number of atoms contributed by the base centered unit cell is equal to 1 plus 1 equal to 2 atoms. So in base centered unit cell 2 atoms are contributed. Like that you can remember, B for base, B for P second letter, 2 atoms. So 2 atoms are contributed by body centered unit cell.
Revision of unit cell. There are 4 types of unit cell based on arrangement of particles in unit cell. Simple cubic unit cell, body-centered unit cell, face-centered unit cell, base-centered unit cell.
Crystal systems. 14 Bravais lattice. Here below is 14 different type of crystal structure. Today my friend will explain you about crystal structure.
Crystal systems. By mathematical analysis, it has been proved that only 14 different kinds of space lattices are possible. In other words, there are only 14 ways in which similar points can be arranged in a 3-dimensional order. These 14 lattices, which describe the crystal structure, are called Bravais lattices.
There are 7 crystal systems based on edge length A, B, and C, and angle alpha, beta, gamma.
In orthorhombic system, edge length A is not equal to B, and B is not equal to C. In orthorhombic system, angle alpha is equal to beta, and beta equal to gamma, and gamma equal to 90 degree. Here, all angle are equal to 90 degree.
There are 4 types of orthorhombic crystal structure: simple cubic, body-centered unit cell, face-centered unit, and end-centered unit cell.
2. Triclinic system.
In triclinic system, A is not equal to B, and B is not equal to C.
And its angle is alpha not equal to beta, and beta not equal to gamma, and it's not equal to 90 degrees.
3. Cubic system. In cubic system edge length, A, B, C are all equal.
And here, angle alpha is equal to beta, which is equal to gamma, which is equal to 90 degree. Cubic unit cell consists of 3 types of unit cell: simple cubic, body-centered unit cell, face-centered unit cell.
4. Tetragonal system.
In tetragonal system, edge length A is equal to B, and B is not equal to C, and angle alpha, beta, and gamma are all equal to 90 degree.
In tetragonal system, there are 2 unit cell possible. One is simple cubic and another is body-centered unit cell.
5. Monoclinic system. Here's simple primitive cell formed by attaching 8 atom at 8 corner of unit cell. Where edge length A is not equal to B and B is not equal to C, and edge length alpha and gamma is equal to 90 degree and beta is not equal to 90 degree.
Similar, we can give explanation of n-centered unit cell. Below animation is n-centered unit cell monoclinic unit cell. Here also A, B, C are not equal to each other. And angle alpha and gamma equal to 90. And beta not equal to 90.
6th, hexagonal system. So this is the hexagon shape. I am attaching here the atom. 6 atoms are arranged at the 6th corner and 1 atom at the center. And another, there is one more hexagon. Same thing I am doing here also. Say I am bringing the 6 hexagon on the 6th corner and one atom at the center of the hexagon. Now I will attach all these lines. Okay. This is x-axis, this is y-axis, and this is z-axis. Okay, so there are 3 axes. So what is there in the hexagonal system? All the edge length A and B is equal, but B is not equal to C. Here you can see here A length and B length both are equal. Okay, here A is equal to B, but if you see the C here, this pink one is not matching with A and B length. So A is and B are equal, but it is not equal to C. Now angle. What is the angle? Alpha and beta angle is always 90 degree, but gamma is 120 degree. So here you can see alpha is always between what? B and C. So in between B and C, you can see here is the angle 90 is there. And beta is in between A and C edge length, and here the angle is 90 degree. So alpha and beta both are angle are 90, but if you see here, that is gamma, here the angle is, it is an obtuse angle, and here the angle is 120 degree. Next is rhombohedral system. In rhombohedral system, we are bringing all the atom in such a way that it form a rhombohedral shape. And what is a rhombohedral? Here the edge length A, B and C all are equal, but what is the problem? Here the angle alpha, beta and gamma is not equal to 90. It can be anything, but it cannot be equal to 90. So such type of structure is known as what? Rhombohedral system. There are 14 Bravais lattice. First is orthorhombic system. So in that there are 4 types are there. All 4 types are there. Simple, cubic, body centered, face centered and end centered. So in this there is 4. Next is cubic system. In this there is 3. Okay, simple cubic, body centered and face centered. You can remember like that. Cubic means 3 types are there. Okay, next one is triclinic. In triclinic there is only one, that is simple primitive unit cell. Another is tetragonal system. In this system there are 2 types. You can remember like that. 4 half is what? 2. So it is there is two unit cell, simple cubic and body center. Okay, in monoclinic there is two. You can remember like that. One is then one ka double is two. So there is two cubic unit cell, that is simple cubic and end centered unit cell. And next is hexagonal system. It is only one type. Next is rhombohedral. It is also one type, simple primitive unit cell. Okay. So there, if you count here in orthorhombic 1, 2, 3, 4. 4 is there. 4 cubic, 5, 6, 7. Then 8, 9, 10, 11, 12, 13 and 14. So there are 14 Bravais lattice, depending upon their position and depending upon their angle, not position, angle and edge length, everything. According to that, there is a different shapes are there. So there are 14 Bravais lattice.
The relationship between molar mass, density of the substance, and unit cell edge length.
So that there is one derivation to obtain the relation between the density of the substance and the edge length of the unit. So this is a cubic cell. If the edge length of the cubic unit cell is A, so if the edge length of this cubic cell is A, so this edge length is A, this edge length is A, so it is a cubic. It is here length, breadth and height all are equal. So we are taking such a unit cell whose edge length is same, that is A. Now, then the volume of the unit cell will be volume. What is the formula of volume? Volume is equal to side. So here it will be here the whole volume of this cubic unit cell will be AQ. Then suppose the mass of one particle is m. Suppose in this unit cell there is one particle and that particle mass is. Next there is if there is a n particle per unit cell. Suppose there are two particles are there. Okay, or it can be more than two, less than two, also anything can it be there. Suppose if I bring this also, so in this unit cell, suppose there are three particles are there. Okay, so what will be the mass if I weight this mass of this unit cell? What will be the mass of the unit cell? The mass of one particle into number of particles. That is written here. Mass into number of particles. So m into n will give the mass of that unit cell. Next, if I give one example, suppose if it is a simple cubic unit cell, there will be one atom. So one atom mass is what? M. 1 into only one particle is there, therefore m into 1 is equal to m mass of this unit cell. Next is one more example, body centered unit cell. You know that body centered unit cell here the one atom is due to the corner position and one atom is due to the center position. So there are total two atoms are there. So one particle mass is m. So there are two particles, so the mass of this body centered unit cell will be 2m. Next.
The density of unit cell, rho. Rho equal to mass of unit cell divided by volume of unit cell, which is equal to m multiplied by n divided by a cube.
So in this, the density of the unit cell is what? Mass of the unit cell upon volume of the unit cell. Okay, so mass of the unit cell in previous equation 1, the mass of the unit cell was m into n. So here we have to write that m into n. Okay, the mass of the unit cell. And the volume also we know that it is a cube. So this will be the equation 2. Now the molar mass of the m of the substance is given by mass of one particle into number of particle per mole. So so symbol is m for molar mass. Molar mass is equal to small m into an Avogadro number, that is Na. Na is what? Number of particles per mole. In 1 mole, number of particles is present is Na. So small m is equal to capital M divided by Na. This is equation number 3. Now, so, I will explain you how the formula has came here. Suppose if I assume that this bottle has a volume of 22.4 decimeter cube of volume. So in that, if I fill any gas or any particle, so if I count that particle, it will be the Avogadro number. That is, it will be 1 mole. And in 1 mole, there is a Avogadro number particles. So what is the Avogadro number particles? 6.024 into 10 raised to 24. So what will be the mass of one particle? If I assume that mass of one particle is m. So what will be the total mass of the particle present in this body or of this volume? So it will be the molar. It is called as molar mass because 1 mole mass. So molar mass means the number of particles, Avogadro number of particles are there. If I weight that Avogadro number of particles, it will be the molar mass. So the molar mass, to calculate the molar mass, you have to multiply small m, mass of one particle, into Avogadro number, that is Na. So here, that's why here below here it is written molar mass is equal to small m into Avogadro. Here also the same thing is written. Molar mass of the substance equal to mass of one particle into Avogadro number. That is number of particle per unit mole. Na is nothing but 6.022 or 24 into 10 raised to 24. This is just for reference. And if I combine the equation 2 and so this is 2, assume this is 3, it is wrong. Combining this 2 and 3, I will substitute the small m part in this equation 2. So instead of small m, we will write capital M upon Na. So the equation will be rho equal to capital M. Instead of m, we will write what? Capital M upon Na. Capital M upon Na is written. What is the remaining part? Small m, we have substituted M upon Na. Remaining part is what? N upon A cube. So here we will write N upon A cube. So what is the formula? Rho equal to Nm upon A cube Na. This is the density of the unit cell.